Good evening, everybody. This is Obi-Wan Pez for N-Simplex Pachinko. We're going to be doing some math tonight, so we're going to look at this. And 26 stacks. Can an nth root be some base raised to a fraction? Absolutely. So most of the time, and this especially happens when we start looking at Calc 2. There's a whole chapter that's devoted to taking the nth root. Oh, goodness. There's a whole test named after it. So the nth root test is designed... Shoot, come on now. Nth root test is designed to test the... come on now. Brain not braining. Almost there. Convergence. There we go. Designed to test the convergence of a particular series that you're looking at. So you've got infinite series, which are going to be... There we go. Infinite series, which look something, roughly speaking, like I goes from 1 to infinity of, let's say 3 to the I times I should probably just look one up instead of attempting to make one up, because my brain's just apparently not working right tonight. So it's cool, whatever. So we'll go like this. Open stacks, Calc 2, table of contents. A. Okay, let's go with nope. So go with something like this. So for this particular thing, we see that like a sub I is going to be equal to 3 to the I times I to the 15th over I plus 1 all raised to the I. And the goal here is to say that, okay, if this is going to, and this probably doesn't have anything to do with your question, but still nonetheless, it's a little bit of fun, for some definition of fun. What we're trying to do is we're trying to take the limit as I goes to infinity of a sub I, and then determine if the ith root of that, take the limit as I goes to infinity, we're taking the ith root of a sub I, and then saying like, as this is going to infinity, what's going to happen to our individual values? If they get within a certain range, they're going to eventually sum up to essentially nothing, and then it's going to converge to a specific value. So we test this, we say if our limit ends up being, let's see, where's the break case? It's 1. Right, absolute value as well. Okay, so if let this be, they call it rho. So if rho is a small number, meaning that it is between 0 and 1, it will include 0 as a possibility. Then this series converges absolutely, meaning that there is no necessary condition under which you need to do any more tests. If rho is between 0 and 1, and including 0, not including 1, then you're good. You could just say, yeah, this thing's going to converge. No notes. If rho is greater than 1, which means that it can go to infinity, or it can be a finite number that's just greater than 1, then this series will diverge. And if rho is equal to 1, then the test is inconclusive. You gotta find yourself another test. So the way we do this in calc is we say, okay, rho is going to be equal to, this is the limit, as I goes to infinity of, so the ith root here, this is a variable root, so people are like, what are you doing? That doesn't make any sense. It kind of does. It's alright. So we take 3 raised to the I times I raised to the 15th, divided by I plus 1 to the ith power. And then we can take this as 1 over I as the exponent. Limit as I goes to infinity. Here we can take I in as the exponent. We're going to get 3 to the I over I times I to the 15 over I divided by I plus 1 raised to the I over I. Which means we get the limit as I goes to infinity of 3 times I to the 15 over I divided by I plus 1 raised to the first power, so it's just I plus 1. Okay, so now the question is, what's going to happen as I goes to infinity? So we can see that we're going to get a 3 up top. That's not going to really change anything. The I plus 1 in the denominator is going to go to 0. And then this thing is the only real weird question that we've got going on. So this is now essentially a tower function. We're saying, okay, what is I raised to the 1 over I going to be? Right, the 15th power doesn't really do all that much in the long run. Eventually, if I get small enough, raising it to the 15th... Wait, no. I is going big. Yeah, the 15 is not going to do anything in the long run because we're going to divide it by some huge, ridiculous number. So if we're taking essentially an infinite root of a number that's going to infinity, we're going to probably get something that's going to 1. But now we have to just double check real fast. So we can go to one of our handy dandy tools and say what's going to happen as we take y equals x raised to the 1 over x. Okay, and as we can see here, this is dropping back down again and heading back toward 1. Y equals 1, right? Goes that way. And we'll call that our asymptote because I'm pretty sure it is. And if we go to like right? Ridiculously large. We'll go to like, okay, negative, nope. Right, 0.9 to 1.1. We can still see that our value here is technically above 1, but it's really close. Right, 1.0001. It's really close at like 100,000. We're getting out that way. There we go. Whoops. Okay, and then if we raise this to the 15th power, this is really just going to delay the inevitable. Right, so our value ends up just being a little bit higher for a while, but it's still dropping to 1 very quickly. So that's going to tell us that the limit of this particular thing is going to go to 1. And so our limit here, nope. We're going to actually use the limit now. All right, the limit is going to be 3 times 1 over infinity. So this is going to go to 0. So then this tells us that the original series here, as infinite as it may be, this will converge by root test. All right. So no. This is one of the reasons why I stopped using I a long time ago, but I still do it occasionally, just out of habit. This is not I imaginary. This is I index. So I is a variable in this sense, and we're using it to index all these values. So we just say that it's going from 1 up to infinity. We're going to literally plug in every single individual value. It's just that we have found a shortcut so that we don't have to do that. We say, all right, we're going to take this series that we have here, and if we want to know what it's actually going to be, we're going to plug in the individual values one at a time. So when I is equal to 1, we end up with 3 to the 1st times 1 to the 15th over 1 plus 1 raised to the 1st plus I equals 2. 3 squared times 2 raised to the 15th power divided by 2 plus 1 raised to the 2nd power. Plus. And then we just keep going on like that for a long time. Until we essentially get it. As soon as it starts becoming obvious like what the series is doing, we can generally stop. In theory, you've also got then the fact that you're going to add certain numbers to these terms for quite a ways before they start like settling down a bit. And the reason for that is the 15th power here. So like I said, I was a little maybe overzealous in using this thing, but yeah, it's fine. No matter what that number is, right, as long as it's a finite number, our constant 15 is going to get outstripped by whatever's happening on the bottom. Because here we're going to get a large number raised to a large number minus 1, essentially. And when the denominator gets really big, then the whole rest of it ends up becoming extremely small. So, extremely long-winded answer for your question, and apologies, but yeah, it works. Trying to look something up real fast and see if I can do it, but... So, 26X, what was your other question that's terribly spooky? There was something that I could do. I don't remember what it is now. What happens when a base is raised to an irrational number? So, I mean, really, it could be any real number. So if you're thinking about, like... Come on now. There we go. What happens when we take, you know, 5, and then raise it to some sort of irrational number, be it pi, be it the square root of 2, be it whatever. It doesn't really matter, right? Like, what does this mean? There isn't really a good, like, concrete answer. If you wanted something that was, like, at least an approximation, you could say, okay, as we're getting values that are closer to pi, we're doing essentially a limit as our value of a over b starts approaching pi. You do like 5 raised to the a over b, and then see what you're getting as you move out like that. This says that we would be taking 5 raised to the a power, and then taking the bth root of that thing. Again, this is a decent approximation. It isn't actually 5 raised to pi, but you could get values that are closer and closer to it. So if you've got all sorts of different approximation values for it, let me see. If I want to do like a Taylor series, we could do a Taylor series. That might be spookier than you're attending. So yeah, I don't know if I have a really good explanation in terms of using irrational powers. Yeah, they're doing the same thing I did. They were like, hey, let's use approximations. If you want root 2, let's do 1,414 over 1,000. And then let's try a different number, and let's try a different number. So this is just using... This is just using, like, basic properties to, like, play with exponents, but it didn't matter, right? Because you could do this as... You could do this with just regular numbers. It doesn't really do anything. Yeah, it doesn't explain anything, really. It's just, we can use a real number. It doesn't matter what number we're using. Yeah. Meh. So if we want like successively better approximations for pi, we could do that by doing like we'll do pi out to n decimal places and then a over b to get a good approximation. So if we have 0 decimal places, this is just 3. So 3 is a nice easy one. It's just 3. And then this could be, oh, you can't see. Yeah. Right, and then we do 5 to the a over b. So in this case, that's 5 to the third is 125. Easy enough. Okay, if we go to 1 decimal place, this is 3.1, and this is going to be 31 over 10. All right, 5 raised to the 31 over 10. Oh, I didn't charge this, did I? Yeah. Pi, nope, 5 raised to the 31 over 10 is going to be 146.8273.679. There's more stuff after it, but it's fine. 3.14 would be like 314 over 100. Again, we could simplify it, but whatever. It's not that big of a deal. 314 over 100 is going to be 156.590. Again, more stuff after that. 3 decimal places is 3.141. Over 1,000. Is 156.8428. Okay, 3.1415. Over 10,000 is 156.96913. And then we could keep going on with this. 5 to the pi, actually. So 5 to the pi is actually 156.9925453. So if we didn't actually have a way to get pi and then just plug it into a calculator, right? Like, hashtag unsponsored. Texas Instruments. Right, if we didn't have a nice way to plug in pi. So, for instance, before digital calculators, right? How did people do this? Or even just at the advent of digital calculators, like how did you calculate pi in the first place? Much less raising pi to something. So again, our calculator can essentially get just a really good approximation for pi, however many decimal places it needs. And then start calculating out, like, can we get something better than this? And then try to get successively better values as we're moving through. I don't actually know, now that I'm saying it out loud, how a calculator goes about solving something like this. Just me personally, like, I don't know how it does it. Okay, yeah, that makes sense. Okay. So the calculator is going with approximations. And it's going to take, you know, x, your calculator is going to take x to the y, and then calculate it instead as a much easier thing. So it's going to take e to the natural log of your x to the y, which then makes it e raised to the power of y times natural log of x. Now somebody in the comments of this thing was saying, well, the calculator's going to do it in binary, so it's base 2 instead. Sure, fine. I'm not going to do that. I don't care. And like any good mathematician, I'm just going to use the natural log, because it's just, That's the easiest thing to do. And I like how it rolls off my fingers. If Megalomorph were here, he would scold me. Or maybe just say, what do you mean? Yes, that's absolutely what I'd do. Okay, so in this particular case, what we were looking at up there was we were looking at 5 to the pi, which would end up being calculated as e raised to the exponent pi times natural log of 5. The calculator can do all of these individual things much easier than it can doing the original 5 to the pi power. And again, this would be in base 2, which would allow this to be 2 raised to the pi times log base 2 of 5. And in fact, any base that you feel like putting in here, that's exactly what it would do. Right, it's still all the same stuff. So the calculator calculates what is the natural log of 5. Then it multiplies it by whatever approximation it has for pi, which again can be a rational function. You could just say, like, you know, here's the 30 decimal place equivalent of this fraction. We multiply that by their natural log of 5, and then raise e to that power, or raise 2 to that power. Again, with digital calculators being binary, it makes it much easier to use base 2 than anything else. But as far as the math is concerned, natural log is by far the easiest. Why is natural log easiest? Well, in terms of the actual calculation, okay, maybe it's not, but in terms of the calculator, in terms of like actual doing out math, I was showing this to my students today. If we take e to the x, that's terrible. If we take e to the x and we look at any particular point along its surface, the slope at any of these individual points those of you who are in calculus, you probably recognize this. If we want to know the derivative of this thing, so again, what is the slope function of our original function? Then we take f of x plus h, which is going to be e to the x plus h. Subtract our original function e to the x, and then divide it all by h. And I did exactly what my students did today. I forgot the other. That is not what I wanted to move. I forgot the other super important part of this. Take the limit as h goes to 0. E to the x plus h is the same as e to the x times e to the h. Again, add exponents when your bases are like. Subtract e to the x and divide everything by h. Equals limit h goes to 0 of e to the x can be factored out, leaving behind e to the h minus 1 all over h. If we put all the h's together, e to the h minus 1 over h just all becomes one thing, and e to the x does not have an h in it, so it doesn't care about the limit that's here. It'll pass right through it. So e to the x multiplied by our limit as h goes to 0 of e to the h minus 1 over h. Need to move that again. Okay, and then when we do this, if we look at, again, this thing, we can go over to Desmos and pick up fraction. Whoops, that is not the right window. Gotta switch keyboards again. Right, we can go to y equals fraction e to the h minus 1 over h. Home. Okay, and we wanted, what is the limit as h goes to 0? Well, the numbers that are getting really close to x equals 0 are getting us a y value that's really close to 1. And again, from like essentially using our squeeze theorem, from both sides we're coming closer and closer to it, and we're getting values that are closer and closer to 1. So naturally, we're going to assume here, right, this starts getting artifact when you get really, really close. So yeah, we're getting values that are closer and closer to 1. At 0 itself, it is undefined. It is indeterminate because we have a 0 divided by 0, so we don't know what value it could possibly even go to until we actually look at it or find another way to eliminate the h that's in there. We can't do that. So we just find what it's going to approach from both sides. We find it's approaching 1. So all this stuff here is going to approach 1 times e to the x, which is equal to the derivative of e to the x. So the derivative of the function is the function itself. This is the only function that is going to ever do that. Almost. You tried. Okay, so that's, again, why I like using natural log. If we ever do calculus on this type of stuff, it's just much easier to use this because then you get the same value that you do for the regular function and its derivative. Interestingly enough, if you do this and you say, okay, what are we going to get if we have not e, but like just some base, b. We're going to add a slider for b. And we're going to let this be I'm going to do a mystery function. Wink, wink, nudge, nudge. You have no idea what it is. Okay. So in these particular values, you can see as we're starting to get higher and higher values, when b is 2, this mystery function value up top is going to be 0.693147. As we move higher than that, as we hit 2.7, this gets really close to 1 because e, the base e, is 2.7, 1828, 1828, 459045, etc. So if I actually manually type it in, 2.7, watch the y equals all the way at the top. Right, 2.7, 1828, 1828, 459045, right? Like after a certain number of decimal places, it's like, yeah, it's close enough to 1. It's just going to be 1. So we have here this mystery function here is getting us exactly the value that we wanted, in this case 0, 1. And as we move it, right, if we have b is 4, if we have 4 to the x as our initial function, then we're going to get our derivative, which is just going to be 4 to the x, times this number. So 1.38629436112, which, right, ends up being the natural log of that base. So if we increase this more, right, we can get a value of 2 around 7.3, which I happen to know is going to be e squared. So if I do, what is e to the second power? This is 7.3890561. Oops. 609. 89. Again, we get a value that's close enough to 2 that it's just going to be like, all right, that's fine. So our derivative function for all exponentials ends up being that if you have the derivative d dx of b to the x, we're going to end up with b to the x times natural log of b. Whatever that b value was, whatever our base is, it's the natural log of that base. And then it also works out the same way if you want to do anything else. So if you wanted to do it in terms of log base 2, you could also do it in terms of log base 2. But it's going to be, what, log base 2 of b over log base 2 of e. So you might as well just use natural log. Could we get a decent approximation for a natural log of 5? Just us by hand. I mean, yes, but told you it was going to be spooky math. So one of the ways that we do this is typically saying, okay, we're going to find a function, which is going to be, we like power series usually, so let's do k. So we avoid the problems from earlier. We want something whose equation is going to be the same. So our power series is a sub k times x to the k. If we want something at, we could argue what values we want here. Alright, a sub k is going to be our kth derivative of the function at that particular point that we want, which again is going to be x equals 5. Divided by k factorial. So this is our Taylor series. And here we were saying that we wanted to, if we're centering it at 0, clearly that's not going to work for a natural log function because it's going to drop off at 0 and have an asymptote. So we can't technically do that. One of the ways we can compensate is by saying that the function itself is going to be natural log of 1 plus x, so that we're just always adding 1 to the inside to make sure that it is, our function gets shifted left 1. Right, x minus -1 does a function transformation to the left by 1. That'll allow us to get a value at 0. I don't really care so much because we're doing a value at 5. We could shift this to e. That could do pretty well. We can't shift it to e squared because that's 7 point whatever I said it was, which would then leave a gap, or 5 would end up being a negative value. So we could either do this just as natural log, we could do it as natural log of 1 plus x, or we could do it as, oh no, it might not be within the, radius of convergence. What is the radius of convergence of power series Taylor for there we go. Yep. Natural log of x at x equals 1. Evaluate the Taylor series. This will get us these values. It's decent, it's approximate. Yeah, that'll work. Okay. Okay, no, it should work. So we'll shift Taylor series out to e to the first which will get us a reasonable approximation at 5. So E is about 2.718. So we're going to be doing, where am I? I'm right about here. No. Okay, so we do this, we say that we're going to go k equals 0 to infinity of the nth derivative, kth derivative, of natural log of x minus e over k factorial, evaluated. All right, a equals 5. This is at this particular point. X equal whatever. Evaluated at x equals 5. Multiply by parentheses x minus e to the k. Yeah, I'm doing like all sorts of I am doing murders here to our notation. So apologies to any actual mathematicians watching this. At this point, Taylor series for n particular terms is going to be equal to of x. We're doing it in general first. Right, f of x is equal to the natural log of x minus e. I don't think anybody's going to care. Right. Somebody's going to come in and yell at me, it's fine. If anybody does have any questions, please interrupt me. So we're going to take this as 0th derivative. So we're just going to take the natural log at, wait. Wait a minute. Might be able to make this easier. And if we make it easier... Oh my god. So many things. Yeah, okay. It's x minus a. The derivatives are just natural log of x, though. We don't have to worry about the minus e thing. Right, so this is just the natural log of x. And we want it when x is equal to e eventually. Alright, zeroth derivative is going to take this as natural log of e over 0 factorial, which is going to be 1. Okay, plus first derivative of natural log is going to be 1 over x. X is e, and then we multiply that by 1 factorial, which is just 1. Plus, then we take the derivative of 1 over x, and we get negative 1 over negative 1 over x squared, so that's e squared, times 2 factorial. Next one's going to be a plus 1 over, we end up dropping our, oh, that's going to be fun. We drop the exponent, it's going to become a negative 2, which switches our sign back to positive. It's going to be e to the negative third, x to the negative third. And then we're multiplying by 3 factorial. Anybody see it yet? I just remembered that. Okay, then minus. We're going to get the 3, negative 3, then comes down from our power and makes it negative 6, because it's now 2 times 3, which is now 3 factorial. The other one was 2 factorial. This was 1 factorial. And this is 0 factorial. In the denominator, we now have e to the 4th power times 4 factorial. Now, the good news is this is definitely going to still converge. All these numbers are going a lot faster. Oh, shoot. Damn it. Okay. Hang on. This is okay. It's salvageable. This is times x minus e to the 1st power. This one is now also times x minus e parentheses to the 2nd power. Nope. This is times x minus e to the 3rd power. This is times x minus e to the 4th power. And so on and so forth. Alright, natural log of e is 1. 0 factorial is 1. Plus. 0 factorial is 1. 1 factorial is 1. This is going to be 1 over e. T sub n of x. We're just letting n go off to whatever value we want it to be. This is x minus e. Okay, we're always going to have x over e. To higher and higher powers, but our denominator is going to keep increasing. This may not be within the... This may not actually work. I don't think it's in the radius of convergence. Okay, so let's take a look at it. This is going to be the sum of x over e minus 1 raised to the kth power divided by k, when all is said and done. Right? So if we take this as a root, we're bringing it back. We go to the root test, and this is going to be rho is x over e minus 1 all over k to the 1 over k. K to the 1 over k is 1. So x over e minus 1 needs to be less than 1. When does that occur? That's when x over e is less than 2. So x needs to be less than 2e. Is that what we have? Yes, it is. Oh, only just. So this may take a very long time for it. Okay, so here's, yeah, this is the good news-ish. It seems like this series should converge as long as x is less than 2e, which again it is, because x is now going to be 5. And 2 times e is 5.4 something. 2 times e is 5.43656. Okay. Woo, only just. Hey, Sorcerer 1. We're doing alright. We're attempting to look at doing a Taylor series to find the values of the natural log by hand, and specifically we're doing the natural log of 5. Like I said, spooky math. How are things going? What are you up to? Have any questions yourself?
Raiding party!
Because this is just for me. Pen Center! Good evening and welcome everybody. My name is Obi-Wan Pez. This is Ensimplex Pachinko. Thank you very much for the follows. Yeah, Taylor Swift got some math lore. So this is Brooke Taylor from 1700s-ish. Hey, Pen Center. Yeah, you too. How are you? Wow. What are you up to? How are you this evening? And those of you who have not met Pen Center, I mean, hey, she's got some fun songs all of her own. If anyone has not yet met Pen Center, please go and check them out. They are an awesome streamer. And I have been in every so often to poke around and ask some questions about math myself. So analysis proof type questions. Yep, nice. Awesome. Anders, very good evening to you as well. Thank you for coming. I will say one of my more favorite Taylor Swift songs is actually written by one of my more favorite bands. This was Aranda. Damien Aranda wrote the song Why You Want to Bring Me Down. And he and his brother Gabe had performed Why You Want to Bring Me Down as like as Aranda, and I absolutely loved it. And then I heard Taylor Swift singing it, and I'm like, the hell, man? And I found out, no. I mean, she paid them. It was she got the rights for it. Okay, so to catch everybody up, we were doing some stuff earlier. One of our other viewers had asked, what are these whole, like, irrational exponents thing? Like, what intuitively does that mean? And I didn't have a good answer. So I said, basically, the best thing you could probably do is come out and say, well, this is sort of like taking a base of 5 and raising it to the 8th power and taking the bth root of it and saying, like, we're trying to find what are some good a over b values that eventually approximate pi. And then the same for square root of 2. So we did some just poking around and said, like, okay, if we go through this, we start doing, like, what's a over b accurate to this many decimal places of pi? So we did 1 through 4. And we got here 4 decimal places of pi. It's going to get you 31,415 divided by 10,000. And it gets you a value of 156.96913. And the exact actual value for 5 to the pi is going to be 156.9925453. Then I said, well, I've never actually thought about how a calculator will actually go through and figure out how to do these irrational things. Like, I had sort of an intuitive sense. It's going to approximate, right? Use a decimal like we did here. But then I went, well, maybe not. So I looked it up, and it turns out that, not really that surprisingly, the calculator is going to take 5, take the log base 2 of it, because it works in binary. What is the log base 2 of 5? Then multiply it by its decimal approximation for pi. Then, or binary approximation for pi, I guess. And then raise 2 to that value to get the full, actually what it's going to be in the calculator. So I hadn't really thought about, like, how the mechanics of all that work. And then I was thinking, how could we find natural log of 5? If we're just going to do, we personally, as mathematicians, are going to use the natural log for everything, even if it doesn't make all that much sense, because, quite frankly, we're just using this. So, like, whatever. So we go through and we say, okay, if we're going to do this, we're going to find the natural log of 5. Then, how can we do it by hand? And I was thinking, probably the best approximation we can find is going to be our Taylor series. So how do we do Taylor series of natural log? We're going to take this as power series a sub k times x to the k, where a sub k is going to be our constants. It's going to be the kth derivative of our function, which is going to be the natural log of x, divided by k factorial. And we're doing out those individual values. We started collapsing this, and then I realized that, hey, wait a minute, this might not actually be within the radius of convergence. So how do we do that? Well, we figure out we did the root test all the way at the beginning of stream. So bringing it back, we said if we take the root test of this thing, every time that we move on to the next term, we've got a 1 over e to the kth power times parentheses x minus e to the k. So those can combine, and we end up with x over e minus 1 to the k divided by k, because we had our factorials here, which were partially canceling. So if we do this, and if we do the root test, where we say, okay, take the absolute value of this whole thing, and then take the kth root, or do 1 over k as an exponent, then we end up with x over e minus 1 divided by k to the 1 over k. We discovered earlier that k to the 1 over k is just going to be 1. And then x over e minus 1, all raised to the k over k, is just going to be x over e minus 1. That's rho, and we notice that rho must be less than 1 in order for this series to converge. So, getting rid of all of our random arrows, we need to let that rho be less than 1. Add 1 to both sides, we get x over e is going to be less than 2, or x must be less than 2e. Since we wanted an x value of 5, natural log of 5, then we end up with 5 is less than 2e. 2e is 2.718281828450199045 times 2 is going to be 5.4 something. So 5 is less than 5.4. Sounds good to me. Whew. Right, so 5 is less than 2e. We've got a check mark on that now because, yeah, we know that's true. Alright, then going through all the rest of this stuff. No guarantees on how fast this will converge, of course, but, you know, right. This is going to be 1 over 2 factorials 2 e squared times x minus e squared plus, this is going to be 1 over 3 e to the third times x minus e to the third minus, oh right, and it's also alternating series, which helps. So anyway, I sort of introduced myself. My name is Obi-Wan Pez. This is NSimplex Pachinko. Those of you who are like, wait, I thought your channel name was NSimplex Pachinko. Yes, that is my location. My actual identity that I wish to have online is Obi-Wan Pez because, quite frankly, I look like a Pez dispenser. The resemblance is more uncanny when my hair is longer, and it was better 10 years ago, but, you know, age. Tariski, welcome. Alright, so we have here 4e to the fourth times x minus e also to the fourth plus dot dot dot. Alright, so we're going to want to figure out what the partial sums of all this stuff is in order to get like better approximations of everything. So we can also do this just in Desmos here real fast. So we can find I could probably do this as a table of values, yeah? Y1 is equal to let's see. I want this, wait, hang on. I need to shift this down. Nope, okay. Alright, whatever. F of x is natural log of x. Turn that off because we don't need it. Shift it up to the top. Y1 is going to be what we were doing there. So this is going to be Taylor series is going to be the nth derivative. How do we do that? Nope. D x1 dx x1 no idea if this is even gonna of f of x 1. Nope. Okay. I kind of thought, but yeah. What do you mean they can't be defined in terms of each other? Eh. Also does f x the second derivative, question mark? No? Doesn't do it either? Try using parentheses. Yeah, okay. That's not going to do it. No. Well, it was worth a shot. Okay. So... Nope. Y equals... What did we say it was on the other page? We summarized this as 1 over e to the k times x minus e to the k with n factorial. That's easy enough anyway. Alright, 1 plus. 1 over e times, and you know what, let's just simplify it. This is going to be 1 over 1 factorial. This is to the first, x minus e minus 1 over 2 factorial x minus e to the second. And actually turn this back on. Question mark. Okay, we're going to copy, let's just copy this whole thing and then affix it to the end. We're going to put a plus in between and then trade this for 3. Oh, you know what? It's not exponential anymore. Or it's not factorial, it's just regular. Man. Okay, and then this is going to be third. Alright, so minus, copy paste. It's going to be 4. 4. I mean, it's not great, but okay. And we're still trying to look for that value right there. Actually, this is around 2.7, right? So, like, the value of this thing at 2.7 is getting us the right thing. It's just now we're, like, starting to stretch out from this point. Okay, copy this. There we go. Plus, copy, change for 5, and change for 5. Minus, paste, change for 6, change for 6. Yeah, this is going to be pretty slow. Plus, paste, change for 7. Change for 7. Minus, paste, 8. 8. So it is very slowly reaching out closer. It's one of the problems with Taylor, is that they do get very slow eventually. That's an interesting band name. Okay. I should really just restart. Yes, so my name is Obi-Wan Pez. This is NSimplex Pachinko. We do math here on NSimplex Pachinko every Tuesday night. And then we also do gaming on Friday nights. Lately we've been doing just a lot of whatever anybody starts talking about. So if anybody has any particular questions about... Usually my expertise lies in like the first 2 years of college level mathematics, but I can usually respond to something with varying degrees of intelligence about a lot of other things. So I don't, generally speaking, do too much above first 2 years of college mathematics. And yeah, it's been a while since I did my master's. I have attempted on this channel to do a little bit of programming, especially with Project Euler. I have attempted to learn some tensor calculus with varying degrees of success. And we do a little bit of math research, specifically as it relates to the Ryohui triangle. Better known to most people as the Pascal triangle, and it's, or my attempt to uncover some of its weirder aspects in higher dimensions. And so hence why the channel name is NSimplex Pachinko, because it's essentially like creating a large n-dimensional simplex and dropping balls through it to see where they all end up. So if it's in higher dimensions, 4 simplex, 5 simplex, it's going to get kind of hard, and I haven't really done all that much. But in theory, I should have a way to get some sort of n-tuple that will list how many, like if you're dropping... it's going to lose its metaphor real fast, but if you're dropping balls through a pachinko machine, right, in 2 dimensions, we all know how that works. It's just the same as the trademarked game on The Price is Right called Plinko. Or if you look at an actual, pachinko machine, it's just got a bunch of nails shoved into it, and balls will bounce off the nails and either go left or right. In 3 dimensions, this becomes a lot harder. I don't, but I should have an object that actually does do this in 3 dimensions. Unfortunately, I requisitioned this thing from our engineering department pre-COVID, and I haven't heard back since. So I've attempted to contact the guy, but it's going to take a long time. So we do a little bit of that, talk a little bit about my specific research. I haven't actually tipped my hand in terms of like the exact thing that I'm looking at, but like I want to see if there's a viable paper in it first, or if somebody's already done this, 2 centuries ago, because that'd be nice to know. But I'm trying to get a particular metric within each n-simplex and try to create one of the sequences that might exist within the OEIS, the Online Encyclopedia of Integer Sequences, and if it's not there, I may have a paper. But I'm still trying to find like the actual sequence and figure out what its terms are going to be before I, try and do anything fancy. So anyway, yeah, Taylor series. So this is going out further and further. It's getting us this thing. We'll call this g of x is this. So I want, like, what is g of 5 going to be? Right. That's going to work. So let's see if this gets any better as we do this to, like, 13. Okay, well, it's not negative 11,000, so that's good. This one's probably going to make it go really big again. Yeah. No, it's only 5,000. 3D plotter. Very nice. I could probably make that work with the bit of research I'm doing, so that could be interesting. Yeah, okay. This is just going all over the place. This would actually work better if I just, like... it might actually work better if I just Python this thing and find the... I mean, it's a function, right? It's not like it's hard. Find the individual values and then find the... find the partial sums as we go out to infinity. So here's the other thing, is that we could get this centered around a point that's a lot closer. So instead of 2.7, we could center this around... I mean, we could center it at 2e. So let's see. If we center this at 2e instead of just e, then we're also going to get more terms on the bottom. So let's do this. So this centers it at 5.4. That should make it way nicer. So I think my hesitation was that earlier I was doing this with hey, how's it going? E to the 2i pi. Welcome back. So my hesitation was earlier I was trying to shift the function itself, and when I was doing that it was like, oh, that's a big no-no because you can't shift it beyond the number you want, right? Because otherwise the asymptote exists and then the number you want is somewhere to its left. So that would not be good. So if we make this e to the e minus 2e to the k, and over here we let all of our derivatives be evaluated at 2e. Yeah, this should work much better. Right, and then we don't even have to worry about this crap down here with the... I shouldn't have erased it, I guess, but it's wrong, so... Okay, and now we can get in here with just some particular changes. So the first derivative of natural log is going to be 1 over... See, this is going to be 2e here. 1 over 2e, and then x minus 2e. Over here, this is going to be parentheses 2e squared. So that's going to be nicer. This is going to be 2e over here. Okay. Parentheses 2e to the third, with 2e there. 2e there, parentheses 2e to the fourth there. Come on now. Oh, epsilon delta proofs. What were you all doing with epsilon delta proofs? Was it like the basic Calc 1 stuff, or was it like number theory and discrete, or real analysis? Alright, so natural log of 2e. It's going to be the natural log of 2 plus 1. Plus sequence stuff, functional limit stuff up to quadratics. Okay. So then here, so there's kind of two ways we can let this go, right? We could say that this is going to now be x over 2e minus 1 is going to be the inside part of the power series, which now would need to be less than 1 if we're going to do the thing. So x needs to be less than 4e now, which it certainly will, because again, x is now going to be 5 compared to e, compared to, okay, 4e is much bigger. Alright, so this is going to be 1, this is x minus 2e over 2e minus x minus 2e squared over 4e squared plus, oh, and another 2 from that. So this is going to be 8. Proof scores. Yep. Different techniques for different quantifiers. Interesting. Okay. Plus, this one's going to be a 3 in the bottom. X minus 2e to the third divided by, this is going to be 8 times 3 is 24. E to the third minus x minus 2e to the fourth, all divided by, this is 16 times 4 is going to be 64 e to the fourth in the denominator plus x minus 2e to the fifth divided by 2e to the fifth is 32 times the 5 from the factorial. 32 times 5 is 160 e to the fifth. Okay, this should be much better. Again, our e and x, or 2e and x are much closer together than e and x. So that's going to change, like, all of this. What do you mean g? There's no g defined? Yeah, no kidding. G of x is equal to... Okay, so this was natural log of 2. Nope. 2 plus 1 plus... The pattern is... This is... x minus 2e fraction x minus 2e to a particular power divided by, in this case, chance and causality. Good evening and welcome. My name is Obi-Wan Pez. This is nSimplex Pachinko. We are attempting to do the natural log Taylor series by hand, which I'm going to question my decision on this one at some point, but it's fine. So I was just doing the natural log of x and then trying to find a decent approximation for natural log of 5. So we decided to switch over to 2e, where everything is centered around. And now it's going to be 5 minus 2e inside the power series portion. And then every of our coefficients is evaluated at 2e. It's not a particularly nice value, but, you know, it's better than nothing. Let's see. Probably. So my actual, I have a small bit of research that I'm doing into using a n-dimensional simplex and doing something, wink wink, nudge nudge, with the Leahy triangle, better known as the Pascal triangle, and then expanding it into higher dimensions. So I'm doing a thing in particular to try and look for a sequence which hopefully is not yet on the OEIS. And if it is not, then I'm going to be writing a paper. I have no idea when, but, you know. Over to E. Cool. All right. And then we're going to do minus. Let's just copy this. We're going to move this into that, raised to the second power. 8e squared. All right, and we should actually look for f of 5 as well, being the actual... Okay. I don't know why I'm surprised. I know that it's going to be really close. It's a Taylor series, right? All right, plus this thing raised to the third power, and e raised to the third power with 24, I believe, was the 24e to the third, and 64e to the fourth is the next one. Yep, there we go. 5 decimal places at the 5th term. So, woo! Yes, I'm sorry. Online Encyclopedia of Integer Sequences. I have actually made several discoveries along the way to what I'm doing, naturally, which all are in there. And so I was like, okay, well, clearly I'm going to have to do something that's like separate from that. The ones that I did find in there were, for instance, the actual values that exist within a within an n-dimensional sequence, or sorry, n-dimensional simplex. If I were to do this in, thank you for the follow. So if I were to actually draw a 3-dimensional simplex, this is where it gets kind of fun. So what happens is, in the Pascal triangle, Leahy triangle, really, what happens is normally you have just a 2-dimensional surface, and if you imagine that as the just these front numbers, right? If you were to drop a marble down a 2-simplex or a triangle that had these particular like pegboard style things, what you're going to see is this what you're going to see is this path that the balls could take as they bounce. Falls in... Whoops, that's not it. Can't go to that one. The paths that the balls could take will follow the either left or right at each individual number. The number of paths that lead to these numbers are going to be given by the numbers themselves in the triangle. That also works in Hey. Yes. Got him. So as we move from the top one, it bounces. There's only one way it can get there, right? Falling from the top. And then as it bounces left, it goes to this one here. There was only one way that it could get there. Again, hitting the top one and then going left. And then if it goes left again, there's only one way it can get there, by making the left and then left again. Or it bounces right, and now it goes again left and then right. There are two ways to get to this 2. It could have gone either left then right or right then left. So 2 ways to get there. And then down to the bottom one again, all the way on the left, you have 1. All the way on the right, you have 2. Or sorry, you have another 1. And then in the middle, it could have gone left, right, left. It could have gone left, left, right, or right, left, left to get to the bottom 3. So this just gets all sorts of crazy when you start drawing in all of the different paths that it could take. All right, so then we do this. And we say, okay, now each of these individual things, if you built them as like a honeycomb, oops. And this one actually is in here. Totally symmetric. It's fine. Play then. Oh goodness. Logic gate circuits. Oh my god. We'll check that one in a couple minutes. So if we did this as a tessellated hexagons and then made these prisms so that they would fall, and now you know where my channel picture comes from, right? The ball would go into one of these things, it would fall through the prism, and then it would land at the confluence point of the next 3 down. So here, it would land here at that point. And then physics takes over, and which way it bounces to which one of these holes will it go depends on a whole bunch of stuff, right? But my goal is to minimize. I wonder if he's making that up. Never. Yeah. So my goal is to minimize the randomness that would, or minimize the non-randomness that would go on due to, like, you know, if it hits the interior of this thing and then bounces left and then always comes at this point with like a sort of, sorry, you're right, a like right side momentum, then it has more of a chance of falling into either the upper or right hole rather than the left hole. And so I want to make it about equal probability. And so I made, or I requested that this thing have a kind of long tube in order to drop down to the next level, hit it at the center point, and not have any like conferred momentum. Or if it is conferred momentum, it's going to be random by the time it gets there. Okay, so we do that. And the idea is to make it as uniform as possible. So, the OEIS has all sorts of stuff, which includes taking these values and saying, okay, I've got 1, and then I've got 1, 1, 1, and then I've got 1, 2, 1, 2, 1, 2, 1, 3, 3, 1, 3, 3, 1, 3, 3, 6, 1, drop down to the next layer and keep going with it like that. So, chance of causality, yes, I had this requisitioned by our engineering department, or I requisitioned it from the engineering department. I have not actually seen a product yet. So I unfortunately requisitioned it pretty much right before COVID. And he was like, oh yeah, it's going to be like a, come back next semester or something like that. And I was like, yeah, sure, no problem. And then we were gone. So, like I said, I still haven't actually talked with the guy. If he's got it, he's got like $200 worth of material sunk into this thing. So, I'd better actually pay him. You'd think he would be knocking on my door. But I mean, I guess it's not his materials. But yeah, so my goal is to show so this is what you get, just like the Liouville/Pascal triangle is what you get when you... Oh my god. Right, this is what you get when you take this a plus b binomial and then raise it to the nth power. This is what you get when you take a plus... Oh my god, come on! a plus b plus c and raise it to the nth power. So all of these coefficients are the numbers that you get from raising a plus b plus c to the nth power. And so I started looking into all sorts of other cool stuff. My ship in Elite Dangerous is named after the other property that I discovered with this. If you decide to not create the triangle by just doing, again, this thing, right? If you do direct sums and try to figure out... Oh. That's not what you meant. Right, you're doing your thing. Alright, everybody, just hang on a minute. I need to cycle some water here, and I'll be back in about 1 minute. So, thanks for sticking around. This is also going to knock out some of our pre-rolls for anybody who's coming in. So, be right back. Okay, hi everybody. So we're back. So, we were talking about triangle. So I found out that if you created the triangle not by just doing our standard a plus b to the n, or if you just took the standard everything is the sum of the two values directly above it, but instead you started taking the triangle and saying, okay, I'm going to now take the two rows that are above any particular number and sum all of them up. So we still get 1, 1, 1. And then on the next one, we're going to get, in this space, this is going to be 2, because I'm adding the two numbers above it. And then over on the other side, again, it has symmetry, so we're also going to get 2. In the middle, we're going to get a 3, because this is summing up all of these values for the next two rows. In theory, this also means then that we're going to sum up everything within a depth 2 triangle like this. So we'd be looking at this 0 here and this 0 here for 3. Karnaugh map. Absolutely nothing. Might be able to look something up, but... Okay, so then if we take that triangle and then we move it down and keep moving everywhere, then on the next row, right, this is going to add the two numbers above it. This is a 3. This should start looking very familiar. And meanwhile, the middle numbers here, to get this, we're going to add, again, 2 rows directly above. There's a 0 here from outside the triangle. This is going to be 1, 2, 3 is 6, plus 1 is 7. So 3, 7, 7, 3. This one is going to be, this one is going to be the 2 directly above it on that line, which makes a 5. And then again, to get this one, we're going to go in this diagonal here. We get a 0 up there. This is 7, 3 is 10, plus 2 and 3 above is 15. So we get two 15s here. And the middle one is going to get us 7, 7, 2, 3, 2 up above it. Which is 14, 16, 18, 21. So this particular thing exists within the OEIS. If I were to go down and just list all of the rows as we go across, the standard Pascal triangle is going to be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, etc. That's in the OEIS. No surprise. This one here is also in the OEIS. 1, 1, 1, 2, 3, 2, 7, 3, 7, 7, 3, 5, 15, 21, 15, 5, etc. Again, it's not really that surprising now that I look back on it, because what am I doing? Well, along the sides, I'm just adding the two previous numbers, which is how we get a Fibonacci sequence. So, right? 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, etc. I want that 8. I don't want all this mess in here. Right, so I dubbed this the much in the same way that this was like a Pascal triangle. I dubbed this the Fibonacci triangle. I think it might also be like Pascal depth 2 or something like that. So I went further, and I said, okay, what am I going to get if I do this? And I did some other stuff. I ended up increasing the number of rows that I was adding up until it became add them all up. So you add up every number that is within a triangle above whatever number you're on. So if I'm trying to find, again, what's in this particular position, I'm going to sum up every number above it and just add up all those numbers and figure out what that is. Now, this is wrong for that, so, because all the previous numbers didn't do that. But something else happens that's kind of interesting when we do it, and I termed that one the Infininachi. I started going a little wild on it. I was like, okay, the next one, when we sum up the 3 above it, I'm going to call it the Trinachi, and then like Quadranachi. And then I got to Infininachi. So it's not really how it is, but nonetheless. So if we do this as like Pascal depth infinity, we start with a 1. We go down to the next row. Again, all numbers above it are summed within its reach. So here we just get the 1 is still there. Everything else outside of that is zeros. Then the next one's going to be a 2 on both ends. And then the middle number is going to still be a 3. I said it was Infininachi. So I said, okay, if you sum up every single number above this one, again, within its reach, it just draws a triangle upward. So that's just going to be these numbers. That's a 4. And same with the other side. And then for these middle numbers, we're going to add up all of these numbers. So this is 2, 3, 1 is 6, 7, 8. So 4, 8, 8, 4. And then the next one, 4, 2, 1, 1 adds up to 8. Again, this should start looking familiar, but now for a different reason. This one right here, we're going to get 4, 12, and 5 is 17, 18, 19, 20. And again, it's symmetric, so the other side's the same. In the middle, we get 8 and 8, 16. 2 and 2 is going to be 20, 23, 24, 25, 26. The sums also get very large very fast. I did this, much to my eternal shame, in Excel. And had to just calculate, like, basically drawing them like this. Like 1, 1, 1, 2, 3, 2, 4, 8, 8, 4, and then it was like I did a formula for each one, sum up all the numbers that were in this particular range above this thing. Yes, it is definitely not the appropriate tool for the job if you want a database for any reason whatsoever. Interestingly enough, the outer numbers become 16. Next numbers over are 28. 12 is 45, 46, 47, 48. And then our two middle numbers are 46. 46, 50, 66, 68, 74, 76. Right, so I just went off from there and just, figured out what all this was. So then I took the sum of each of the rows. 2, 3, 2 is 4, 7. 12, 12 is 24. 40, 56, and 26 is 62, 82. I'm probably going to make a mistake here, but it's fine. 76 is 152, and 96 is going to be 248, and 32 is 280. Something like that. Double check me. So anyway, I did this on all of the previous ones as well, and I noticed that there was a ratio between all of the sums. So our ratio between the first two is going to be 2 to 1, and then it was going to be 7 to 2, so 3.5. Oi, come on now. And then 24 to 7. And then 82 to 24 is 41 over 12. And then 280 over 82. So I don't know what that is. 24 over 7 is 3.42857. 41 over 12 is 3.416 repeated. And 280 over 82 is going to be, oh good. It's going to be 3.41463. A bunch of stuff from there. So if we take this value and we look down further, like, you know, go to like the 100th row or something and find the ratio between those two values, it ends up with a particular number. And then all of our, like, all of the other ones do the same thing. They all approach a particular value, whatever it is. And then all of them, as we go across, also are going to, like, the ratios from each individual one end up also approaching this value. So it's like 3.41 something or other. I don't remember exactly what it is. I need to run it again, or steal these files off of my work computer before I leave. So actually, hang on, do I have it? I might just have it in a research folder. That's a modulus thing. Nope. Huh. Yeah, I think it's just in my... I think it's only on my one at school, which is too bad. Huh. Alright, cool. Not really cool, but... oh well. So my ship name in Elite Dangerous is or the call sign, something like that, is 1 plus square root of 3, because it's one of these numbers and I don't remember which one it is. But or maybe this is 1 plus 2 square roots of 3. It's been too long. No, it's 446. Alright. 2 plus the square root of 3. That's closer, but it's not right either. Yeah, I'm gonna have to redo half this stuff, I'm sure. So, yeah, I named my ship Ensign Plex Pachinko and had the call sign 1 plus the square root of 3. Because it's like I said, it's one of these numbers. I can't remember exactly which one it is. But now I want to like extend that into 3, 4, 5, etc. dimensions and see what I can do with it. See if it's going to come up with something interesting. It probably will come up with like a specific single value if it's going to converge. So another possibility is that it will diverge as we start going out into higher dimensions. I don't know. Makes it interesting. Woo! Yeah, ended up getting the Taylor series way closer this time, so that's good. Alright, I'm gonna have to look that up. Use a minimum number of logic gates. Oh, fun. Yeah, I definitely don't know anything about this. So it looks like... Is that Khan Academy? It is not. The Organic Chemistry Tutor on YouTube apparently has a good, or at the very least popular, K-map lecture. Principal component analysis. You know, the further you get into these classes, the more the answer is just going to be no. Machine learning and data mining. Okay, well, that's at least sort of in where I had been at some point during my master's. Okay, the principal components are eigenvectors of that data's covariance matrix, so that's good. Principal components are often computed by eigendecomposition of data covariance matrix. So So the next question is, how do you get the covariance matrix for a data set? I don't know how to do that. Entries in a column vector are random variables. Finite variance expected value. Covariance matrix is the matrix whose ij entry is the covariance. Helpful. Or expected x of I minus expected of x of I. Oh dear. Times x sub j minus expected of x of j. Ugh. That's been far too long. Covariance matrix appears to be the product of two diagonalized matrices times one that has its main diagonal 1 and row. Marginal variance? Question mark? Row just kind of seems to be jumping out of nowhere. Cool. So you're going to need to explain the covariance matrix and like how to find it. Once you can do that, it looks like that is not particularly going to be difficult. You need to do some work with the eigenvalues and eigenvectors of that particular matrix. But I can't. Like, apart from being able to find the eigenvalues and eigenvectors, no. Principal components of points in a real coordinate space are a sequence of p unit vectors where the ith vector is the direction of a line that best fits the data, while being orthogonal to the first I-1 vectors. Yeah, I'm not going to be able to help you with any of that. So again, you're just going to have to compute the covariance matrix with that given data, and then calculate the eigenvalues and corresponding eigenvectors of that covariance matrix. Then it wants you to normalize each of the orthogonal eigenvectors, turn them into unit vectors. But I can't help you. And then turn everything into an ellipsoid fitted to the data. Yeah, ChatGPT does a great job with mathematics. Oh. Yeah, it's so wrong 99% of the time. It might only be a little wrong, but usually you try to get it to do any sort of mathematics whatsoever, it just balks the entire time. Let's do the language model. I'll tell you what you want to hear. If anybody has any other questions, let me know, because still got some time on the clock for me. Give or take. So when we're trying to do, like trying to find derivatives of any particular function, we're using the limit definition of derivative. There's a couple of ways we can go to actually solve the derivative for y equals the natural log of x. First way is actually use the limit definition derivative. As much fun as it is, take the limit as h goes to 0 of, in this particular case, we've got natural logs which are connected by subtraction. So the natural thing to do here is to connect them. And then here, multiply this by 1 over h rather than divide by h. Reason being, come on. Yep, sorry I can't be of much more help, but it's one of the things. Okay, so if we take the limit as h goes to 0, in this particular case, we're going to notice that here our natural log can also be rewritten as here 1 over x divided by 1 over h raised to the 1 over h. If we let, oh, come on. I don't know why this is having so much trouble tonight. It happens almost all the time, eventually, but like... Right, if h is going to 0, then we could also let 1 over h go to infinity. So that means that we could take the limit as now not h goes to 0 or 1 over h goes to infinity, but now if m is just 1 over h, this is m goes to infinity. And that's going to be our natural log of 1 plus 1 over x over m, all raised to the m. And this is the definition of e. So we could let the limit as m goes to infinity come through the natural log to the inside, and then we've got the limit as m goes to infinity of 1 plus 1 over x over m to the m, or over m, all parentheses, to the m. And when we do that, again, that's the definition of e. It's the natural log of e raised to the 1 over x. Whatever's in that position in the numerator of that particular fraction ends up being the exponent on e. Oops, no, not to the m. That was already used in creating e. So this means that now we've just got 1 over x. That's it. So if we had y being the natural log of x, we now have y prime being 1 over x. Alternate method of doing this is that we say, okay, well, let's say that, okay, natural log is the inverse function of e to the x. So that means that e to the y is equal to x. Right, we did this in pre-calc. We did the trading around of our logarithms. So if e to the y is equal to x, I can take the derivative of both sides. And I'm going to use the generic derivative operator because that's the way I do things. Here, the generic derivative of e to the y is e to the y, just like we did before, right? Derivative of e to the x was e to the x. However, in this particular case, we do need to use the chain rule and say that the derivative of the interior portion of this function is just going to be dy. Is equal to the generic derivative of x is dx. That's it. Then we're going to swap these around and make it dy dx. Is equal to 1 divided by e to the y. Or we could do e to the negative y. Let's not make it any harder than it needs to be. So with that, we now know that dy dx is equal to, well, y was just natural log of x from the beginning. So this is negative, or e to the negative natural log x. And that means that we have e to the natural log of x raised to the negative first. And e to a natural log, those are inverse functions of each other, so they go away. And then we're just left with x to the negative first. So dy dx, y prime is just going to end up being x to the negative first, or 1 over x. Right, same thing. I proved this one by accident this morning, doing our limit definition, because I was like, there's no way we can do this. And I was like, wait, we're subtracting these. Huh. Students started laughing. I'm just like, yeah, okay, I deserve it. Okay. If anybody has any more questions, let me know. Otherwise, we will... Yep. See you to the 2i pi. Otherwise, we will raid over... I don't know who's on tonight. Let's see. Games, games, games. What else we got? All of our friends are on tonight. Science is doing Halloween Spooky Science. And it looks like everybody else is doing games, and more games. So, okay. We're gonna head out and see Science then. Hope you all are having a good week, and we'll see you on Friday for more games. We're doing, well, we were doing all sorts of spooky stuff. We'll probably be playing some Elite Dangerous, and or trying to finish Control. No, we finished Control. Right. We'll see what else is on the docket. See what else is coming up soon. So, hope you're all having a good week. I'll see you on Friday for those of you who are going to be in for games, and I'll see you next Tuesday for those of you who are going to be back for more mathy stuff. Thank you very much for the raid to Penn Center, and thank you very much for all of the new follows, for everybody who came in and said hi. So, hope you all have a great time. This is Obi-Wan Pez for NSimplex Pachinko. Have a good night.